Hey guys, hope you're doing fine. My name is Nishant and we are at day 24th of June LeetCoding challenge. Let's look at our question. Unique binary search trees. Given n, how many structurally unique BSTs or binary search trees that store values from 1 to n? Okay, so we are given a value n and we need to find how many unique binary search trees we can form if we are having n nodes value from and having value from 1 to n. So okay, let's look how we can solve this. Okay, let's suppose we are given n equals to 4. Okay, so we are given 4, that is we have values of 1 2 3 and 4. Okay, so we have 4 nodes having values 1 2 3 and 4, and we need to find how many unique binary search trees we can form using these 4 nodes. Okay, so we'll use dynamic programming to solve this question. So we'll create an array of size n plus 1, and that is 0 1 2 3 and 4. Okay, so this array will store our answer for each number of nodes. Okay, so for 0 it will always be 1. So when we have 0 nodes, that is we can still create a binary search tree having root as null. Okay, so the answer is 1. And if we are having only one node, again the answer is 1. Okay, so for 0 and 1 the answer will always be 1. So now what if we have only 2 nodes given? Okay, so let's forget about the nodes 3 and 4 for now, and let's concentrate on number of nodes given is 2. Okay, so we have 2 nodes, that is 1 and 2. Okay, so for this we can now see that we can select any of them as root. Okay, so first we select 1 as our root. So 1 is our root, and the remaining elements, that is 2, will be on the right subtree, will be in the right subtree of 1, and the uh, null node, or we can say 0 nodes, will be on the left of 1. Okay, so uh, so 2 will be here and one null will be here. Okay, so this is one tree possible for this combination. So the number of possible combinations will be when we have 0 trees on the left and we have only one tree on the right, only one node on the right tree, that is 1 and 1. So 1 multiplied by 1, that is 1. Okay, now now let's select 2 as our root. Okay, so when we select 2 as our root, we have only left with the possibility that the 1 can be on the left subtree and 0 on the right subtree, that is null. So again we have one node on the right subtree and one on the left subtree. So the value of 1 here is 1, and the value of 0 here is 1. So 1 multiplied by 1 is again 1. So just now we're gonna add them up, so the answer is 2. So if we have only 2 nodes, we can have only 2 unique binary search trees. Okay, so we will update our answer here. For 2 it will be 2. Okay, so let's go for 3. Okay, so now we have 3, so we have 0 1 2 3 and 0. So now what we do is we select 1 as our root now. So if we select 1 as our root, so we have possibility that 2 and 3 will be on the right subtree and 0 will be on the left subtree. So now we can consider this 2 and 3 as 1 and 2. So since we have only two nodes possible on the right subtree here of 1, so 1 and 2, we are considering this 2 and 3 as 1 and 2. So for 1 and 2 we have already calculated that the unique possible trees possible here is 2. Okay, and for here it's 0, so it's 2, and for 0 it's 1. So 1 multiplied by 2 is 2. Okay, so when we fix 1 as our root, we can have two unique binary search trees possible. Okay, so for 1 it's 2. Okay, so now what we do is we fix 2 as our root now. Okay, so for 2 as our root, so 2 we can have 1 here and only 3 here. So the possible number of unique binary search trees, whatever we have, number of nodes here and number of nodes here. So number of nodes on the right subtree is 1 and on the left subtree is 1. So whatever is the value of 1, it is 1. So 1 multiplied by 1 is 1. So if we fix 2 as our root, we can get only one unique binary search tree. Okay, so now it's time to put 3 as our root. So we put 3 as our root and we again have 0 0 nodes on the right subtree and 2 nodes on the left subtree, that is 1 and 2. So for 1 and 2 we have already calculated that if we have only 2 nodes we get 2 binary search trees. So the total combination will be 2 multiplied by whatever be the value of 0, that is 1. So 2 into 1 is 2 and we add this to our answer. So now we fixed each node as root one time. So now our answer is 5. So if we have only 3 nodes possible or given, we can make 5 unique binary search trees. So the answer is 5. Okay, now let's check for 4. So let's now check for 4. Now we have 4 here. Okay, now let's fix 1 as our root. So if we fix 1 as our root, so now we have null on the left subtree. Okay, and we have 2, 3 and 4 on the right subtree. So now we can assume this 2, 3, 4 as 1, 2 and 3 and put them on the right subtree of 1. Okay, so for 1, 2 and 3, that is 3 nodes, we have calculated that when we have 3 nodes we get 5 as our answer. Okay, so we can make up to 5 unique binary search trees on this right subtree, and here is null, that will be 0. Okay, so 0 and 3. So for 0 the answer is 1 and for 3 it is 5. So 5 multiplied by 1 is 5. Okay, so when we fix 1 as our root we can get 5 possible unique binary search trees when we have 4 nodes. Okay, so now let's move on to the next node and fix 2 as our root node. Okay, so we fix 2 as our root node, so 1 will be here, and now let's assume this 3 and 4 as 1 and 2. So this 1 and 2 will be on the right subtree of 2. Okay, so the number of nodes here is 2 and the number of nodes here is 1. So for 2 we have already calculated that the unique binary search trees possible is 2. So 2, and for 1 it's 1. So 2 multiplied by 2 is 2. So when we fix 2 as our root, we can get only 2 unique binary search trees. Okay, let's move on to 3 as our root. So now we fix 3 as our root, so we can get only 4 here, and here we can get 1 and 2. So for 1 and 2 we already calculated that whenever we have 2 roots, the answer is 2, and whenever we have 1 root, the answer is 1. So the total combination possible is 2 multiplied by 1, that is 2. Okay, so now let's put 4 as our root. So now 4 is our root, so 4 is here, and here will be a null, and for here and for the left subtree the values will be 1, 2 or 3. Okay, so this is it. For 3 we have already calculated that the answer is 5, and for here is 0, and for 0 is 1. So 5 multiplied by 1 is the total combination possible, so that is 5. Okay, now we have done that. So for the answer for 4 is 5 plus 2, and it's 14. Okay, so for this is 14. So at the end this 14 will be our answer. For number of nodes for the possible unique binary search trees is 14. Okay, let's code this. So we'll create our vector or array of size n plus 1 and initialize its value, all the values to 0, and we put 0 and 1 as 1. Okay, since a null is also a binary search tree, and if we have only one node, that is 1, the number of unique possible binary search trees is 1. Okay, so now what we do is we go from 2 up to n, and we calculate each time the number of nodes is now 2 up to n. Okay, so and the second loop is just putting 1 by 1 from 1 up to n as the root. Okay, and for our answer, dp of I is just add all the possible combinations we did for by setting each time a node as root. Okay, so it will be dp of j multiplied by dp of I minus j minus 1. Okay, so if we put 2 as our root, so the 1 will be on the left subtree, and the remaining elements, that is I minus j minus 1, will be on the right subtree. Okay, so this is our code, and just return dp of n as our answer. Okay, let's check this for 4 as well. Should be 14. Okay, There's some error somewhere. Okay, this should be J. Okay, let's put what if n is negative? We just return 0. So should code. So 514 looks good. Let's submit this. Okay guys, that's accepted. Link for the code is in description. Thanks for watching. See you next time.